I want you to work through the 3 images I'm going to show, determine whether they're at equilibrium or not. So you need to do some work first on that if you haven't already done this. Did we already do this? Did we complete this? I get a couple fun looks. It's been a week. All right, so go ahead and try to answer this question, and then there's 2 more diagrams that I'll show after this. So go ahead and do the pre-work you need to. Meanwhile, I'm going to try to hand out your stuff you turned in.
This that you want?
Why didn't you just send me a PDF?
I was lost. I didn't know what to do.
Okay. Thanks.
Yo.
I'm sorry, I'm trying to.
All right, we have 22 responses, another 30 seconds. All right. You guys pretty confident in this? We have a mixture of answers, so that's not super confident. All right, what steps do we need in order to answer this question? Let's hear the process. Go ahead, Tripty. Why do we need to find K? Great. So if we don't know what the equilibrium constant is, we can't determine whether what we see here is at equilibrium or not. What did you find for equilibrium constant? Say again?
0.4285.
Okay, what does that tell us? Right off the bat, what information do we get from seeing that value? Say again? It's less than 1, but it's somewhat close to 1. So what does that tell us? The reaction lies slightly to the left. It means it's slightly reactant favored. Okay, that's all stuff I want you to get right away once you determine the equilibrium constant. Okay, so then we use that to then look at this reaction and say, well, are we there? So can I hear from someone else? How did we look at that image and determine whether the reaction is at equilibrium, needs to go to the left, to the right to reach equilibrium? New voice, new voice, new voice. Bria?
You said look at the image, right?
Yep.
Okay, so you looking at the image, you have more red than blue, and so to reach equilibrium, you have to produce more blue.
Okay.
You want to produce more product.
Well, how do we know? How do we compare? You say we have more red than blue, but what are we comparing that to?
To the right reactants to product.
Yes, but we need to be more specific. Ruby, you want to add to that?
There's 3 blue. Yeah, so I did 3 over 7 because there's 3 blue and 7 red.
What did you just calculate?
Products over reactants over
That's our reaction quotient Q. All right. So what would happen if this equaled exactly 0.428? What can we say? What answer would that be? We're at equilibrium. We don't need to do anything else, right? But we're not. 3 over 7, what does that fraction give us? Does it really?
Yeah.
Okay, I should know my math better. Okay. So, is the reaction at equilibrium, or does it need to go to right, left?
Let's say equilibrium.
Okay. I think that reaction is at equilibrium. All right. Let's take a look at the next one.
Welcome back.
Shake a little rust off my head. So I'll give you guys 30 seconds to answer this one. More?
More red. There has to be more.
Uh-oh, past 30.
Wait, it's on the left.
And we're closing out. All right, what do we do here? Shanaja, what did you do? What did you do to start setting it up? Okay, so is our K different? What was it, 4285? Okay, and then what did you need to compare in order to determine if this is at equilibrium or not? So what is Q for this one? 4 over 6? Which is 0.6
repeating.
So is that at equilibrium? It's close, but it's not. So in order for this reaction to reach equilibrium, what has to happen? Because our Q is not the same as our K. I see some people pointing this way. What do you think? So this number is larger than that, which means that we have to convert some of our products to reactants. It's actually kind of easy to see because our last one was a 3:7 ratio, and that was spot on for equilibrium, right? So if we just took one of the products, one of the blue, and made them a red, we would have the exact ratio that gives us Q would then be equal to K. So in this one is the reaction will proceed left. It will consume products to generate reactants in order to get to equilibrium. And our last one. Thirty seconds. We're over 30 seconds. Closing out. All right. Narina, what were you going to put, and how did you approach it? You said your Q is what?
Q is 0.25.
0.25. So you have a 2 to 8 ratio? Does everybody agree? So then, what does that mean? So Narina, can you complete the sentence of what we can conclude then?
Q is less than K, so it's
I couldn't hear you.
Q is less than K, so it's reactant phase. The reactant phase is product.
Well, right now we have more reactants compared to products compared to our equilibrium. So what has to happen for us to reach, for Q to migrate towards equilibrium? So maybe let me write out the ratio so we can look at it this way too. So Christina, can you add to what Narina's saying?
Basically, I think she's saying that it needs to move to the right.
Okay.
So isn't that product paper? Is that what it is? I don't know how to word it.
So careful. If we say the reaction is We can say the reaction is product favored or reactant favored. It lies to the right or it lies to the left.
Okay.
That's different from to reach equilibrium, we have to proceed one direction or the other.
Okay, so it's gonna move to the right.
So I'll draw this in 1 second.
Okay.
Kayla?
I was gonna say it has to run forward and the reactors have to be consumed to produce more products.
Perfect. In order to reach equilibrium, Kayla said it perfectly, we have to consume reactants to generate products, and that will get us to that 3:7 ratio again. So the reaction will proceed to the right. All right, questions? So maybe I'll just show really quickly, if we were to draw a Gibbs free energy diagram for this reaction, talk to your neighbor about what it would look like. What would the Gibbs free energy diagram look like for the reaction we were just discussing? Go ahead and draw it.
You guys were saying that people are not because it leans more to
All right, one of you volunteer to draw.
She draws straighter. I know how.
You don't straighter. You
Do it, Aurora. You have the pen. I'm not touching it. Caught it.
Don't break the pencil. Go ahead, Aurora.
You got this, man. I have faith
All
in
right,
you.
are you agreeing with your neighbors? Rate your confidence for Gibbs free energy diagrams. Highly confident, not so confident, really unconfident. I only see like half your guys' thumbs. Okay. Aurora, can you describe why you drew the diagram you did?
Because it's slightly less than 1, it must be on the
What is slightly less than 1? Our equilibrium constant was 0.4285, I think, right? It was a 3:7 ratio. So does this reaction lie to the left, lie to the right, or in the middle? Are there more products or reactants at equilibrium? There's more reactants at equilibrium. Reactants are always the left side of an equation, right? We have A goes to B. So there's more of the thing that are on the left. The reaction lies to the left. So then the question is, how does the diagram support that? If we start with only reactants, we would start way over there. That would be our Q if we had only A. In order to reach that equilibrium, the reaction has to proceed downhill until we get Q is equal to K. You drew the minimum very close to the middle. Why?
slightly off.
So if we're in the middle here, that would be a K of 1. We know that the K is slightly less than 1, which means it favors reactants. It lies to the left. The minimum lies to the left of the middle. So that's kind of how all these things connect. So I'm hoping the Gibbs free energy diagram will give you some context for if we find Q, where is that compared to our K? So in those different examples, the first Q, how did that compare to K for that first set of diagrams? The first one, we had our Q was exactly equal to K. That means we're not going to generate more reactants from products or products from reactants. We're already there. The second one, I think we were past. Is that right? It wasn't that much past it, right? But it was a little bit to the right. So our Q was over here. So in order to get to equilibrium, it's going to have to roll downhill. And it's going to have to get Q equal to K by converting some products into reactants. And it's going to move to the left. And then our last one was just somewhere over here. Our Q had slightly more reactants and products compared to our most stable mixture of reactants and products. All right. So before we get into too much more, I know that there was some frustration with the homework today. It seems that it was a system issue because I regenerated the homework multiple times and the pre-class quiz was just defunct. I am open to suggestions via email or discussion board of how to give appropriate credit for that. If I just wipe the whole assignment and the people who did try, then it doesn't reflect what you want. If I give everyone credit, then that's not fair to the people who tried it and others who didn't. So I haven't really figured out how to be fair in giving of credit for this assignment. I hope that you are at least able to go and to kind of work with the ICE tables and Q versus K, 15.3 and 15.4 in the book. And I apologize for any inconvenience it caused. So let me know if you have ideas of how to be fair in assigning credit for the work that you did. Some people did the whole thing and it showed up as you didn't even try it. So we are aware of the problem. Hopefully that is the only assignment that this will happen for the semester. And anything else you guys want to share with me, feel free to share offline. Just know that I'm aware of it and I'm trying to work with Cengage to make sure that doesn't happen again. Second thing, people have asked me what to do for study tools. There is a discussion board post about this, started by Mohammed. So you can go and check out some of the things that we talked about there. You can add your own suggestions. One of the ones that's pretty valuable is, I don't know if you guys use the study tools in Cengage and OWL. I think David was the one who showed me this. So if you click on study tools, you can actually go into specific chapters. I don't know exactly how this all works. Maybe it was the last one, actually, it was. So in study tools, there's this guy right here, study plan for our book. And then you can go in chapter by chapter, and you can practice. These are the adaptive study plans, but here it gives you access to them as a not graded component. It's always better to do problems you haven't seen before. New numbers. If you go back and redo the worksheets we've done in class, not only do you have the numbers in front of you, but you've started it before. So even if you covered up all the individual steps and the numbers you've written out, it's still not going to be as valuable as getting a new problem that you haven't seen in a while or haven't seen at all. So I really advise testing yourself. What am I capable of? What am I not capable of? There's some things we haven't done in here, so that's going to be a part of the filtering out you're going to have to do. But hopefully it's more valuable if you kind of go through and test yourself. Kayla?
On the pre-quiz, it was like about a rice table and a quadratic formula. Is that going to be on this thing?
I'm getting there.
Oh.
Exam 2. Today's class material will be useful to give you a further grasp of equilibrium constants, but I'm not testing you on ICE tables or rice tables, whatever you want to call them, and I'm not testing you on KSP or specifically Ka, but I'm trying to contextualize what equilibrium constant means, how it can be used, and how we want to think about that Q versus K Gibbs free energy diagram from a numeric standpoint as well. We are having a scratch-off component of the exam. What that means is that if you finish at 60 minutes or before, that room will become vacant at 7 p.m. So at 7 p.m., leave all your things here. You're going to turn in your Scantron and your short answer. You're going to take your multiple choice handwritten part of the exam with you over there. We're going to put you into random groups of 3 people. Then you're going to work on a subset of those problems that are multiple choice, the hardest ones out of all of those. And you're going to have to come to consensus on what the answer is. That consensus is then going to have you scratch off A, B, C, D, E. They're going to be like lottery ticket, right? So you scratch off the letter that you think is right. If there's a star underneath it, it means your group got it right. You get maximum credit. If not, you have to recalibrate, talk to your group, and then try a second time. And you'll get a little bit less credit each time you try. If you do better on that portion of the exam, the group stage, then your individual exam, it counts as 10% of your exam. If you do worse on it, or you decide not to take it, then it doesn't count at all. Then your exam score is your exam score. Question, Josh?
But your tests are usually way longer than you expect.
True.
Okay.
I'm trying to be cognizant of that. Priya?
Okay, so I have a question. So you said if you finish in the 60 minutes, you then can go over there.
If you finish at any point after 60 minutes, and we're still here, you can go over there if there's still people to do the group work with.
So how is it fair if other people are getting extra credit, but some people...
It's not extra credit.
Oh, it's not part of extra credit?
Nope.
Oh, I
If
thought that
you-
was extra. Okay.
It can count as 10% of your total test score. So let's say you get a 70% on your individual test, and you get an 80% on the group stage of the test. Then that 80% counts as weighted as 10% of your exam score. The 70% is weighted as 90% of your exam score. If you would rather spend those 15 minutes work on your own tests and get your own tests to a higher level, then that's your prerogative. That is a guarantee that your score is going to be affected by your work. Over there is a good chance that it will be affected, but it depends on how it works in the group. So I will try to write the test so that you should all finish in 60 to 65 minutes. It's challenging to estimate how long everyone takes on tests, so I will try my best. We also have our first Friends of Medicine seminar series. I am stoked. We have 5 separate days in which we have a researcher and someone on the clinical side coming in talking to you guys about their career path, and you guys get to ask them anything you want. So Wednesday is our first day. I know it's not ideal being right before an exam, but I highly encourage you to try to think about ways to get there if you're interested in career medicine. So the researcher is talking about how she uses viruses in order to try to influence the course of ovarian cancer. So she uses viruses as a delivery mechanism to get treatment to the site of disease. And then there's someone who is a survivor who's ovarian cancer. We're going to talk about the pathway that she had going from being diagnosed and what treatments are like, and all the way to getting through the other side. Next Monday we have the second one. All these are 4 to 5:30 in this room. I will be providing food. Hopefully I will not be paying for all of it myself. I think there's people that are going to chip in. UAMS might some, and UALR might some. So next Monday is going to be a researcher who studies how parasites influence vasculature, both blood vessels and your immune system. That's my wife. And then the other one is an English-trained general medicine doctor, and he is going to talk about the national healthcare system there, how it compares to the American system. He now works in rural health in Oklahoma at a community health center, and so he works with people who can't necessarily afford to pay for healthcare, and so there's a lot of interesting conversations that come out of that as well. So those are the 2 upcoming ones, and then after that, it's every Wednesday for the rest of the semester. There's 3 more. I would really love it if you guys could go to the website if you're going to attend, or else there will not be enough food, I promise you. Easiest way to get there is just Google UALR STEM Education Center, and then here there's a Friends of Medicine link on the left, and if you click on that, then there's a place to RSVP, and I'll try to keep this updated with who's coming. There's links to the individuals, so you can go to their websites if you're interested in seeing who's coming. Any questions about the seminar? Yeah.
Is there a cutoff time that you would like us to come in and listen? Like, probably just a couple minutes late? I don't want to be disrespectful to anybody.
No, so the way it's going to work is the first 40 or so minutes will be the people taking turns sharing their story, and then afterwards it's a panel discussion, just open for discussion. So we'll try to start them probably pretty close to 4. Maybe they'll grab some food before, and then they'll share their stories one at a time, and then we'll have panel discussion after that. So if you can only come at 4:45 but you want to be part of the panel discussion, you can come in and just try to be mindful of the questions you ask. They might have already talked about that kind of stuff, so you might try to grab them afterwards or something like that. We will wrap things up by 5:30 so that we have a chance to wind down, and then class can start or the exam can start after that. All right. Supplemental instruction will be occurring this week. I remember during exam week last time there was a bit of confusion, so unfortunately we don't have the luxury to just take a week off. We did take a week off, right? Like a whole week off. We didn't do any supplemental instruction the week before we left or last week. So we're going to be doing one on acids and bases, which is going to line up with what you're doing in the lab and what we're doing in class next week. All right, so my goals for today are what we did already. Predict which direction a reaction will proceed to reach equilibrium. Determining K, what is Q, how does Q compare to K, what does that really look like, what do we call that? The reaction lies to the left, lies to the right, proceeds to the left to get to equilibrium, proceeds to the right to get to equilibrium, those kinds of things. We are going to be doing some ice tables with the reactions in order to calculate equilibrium concentrations. Use that to determine pH of a solution. And we're going to then talk some about equilibrium constants for acids, solubility, and molar solubility. So calculating and then kind of thinking about that. Basically all this is equilibrium constants. And so I want to show you a couple different examples of where we can use these. All right, here we have a chemical reaction. I want you guys to determine what the equilibrium concentration is of H+ ions in this reaction. And I believe you need that. way it helps, make sure to raise your hand if you get stuck.
So the way it should be. Yes. So you should find out what the beginning.
The reactants are negative, and then
So F should be 0.
and then the compressed coefficient is just specified. Okay, so
No, 8.
okay. And then our initial will be 0,
0.5. Minus x plus x plus x. Unless it's actually listed, it's 0. So that's
Okay. Send me a picture of that. I don't know that because certain people said it, well, it didn't even show that they did it.
I mean,
So pretty go back to 8th grade. I just told you. Plus, I already, yeah.
Right, so I think what they're saying is that right, so that's how it
Been too long, huh?
yeah. Sometimes
All right, it's been a while. Before everyone goes and does a quadratic, let's talk through this instead, all right? What is the first kind of step we do to set this up? The pre-class quiz give you a little bit of this, right? And then a little bit on the homework? Maybe? So we need an ice table. The ice table says we're taking hydrofluoric acid, really nasty stuff, and we're putting it into water. What's our initial concentration of all of these? Josh?
So shouldn't H and F be 0? They haven't formed yet, but then it says 0.5 HF, so that's the initial.
Great, I just want you to use units and charges. So 0.50 molar is our starting concentration of the hydrofluoric acid where they're together. The question is, how far does this reaction proceed? How much do they separate? Before we do any calculations, what do I want you thinking about?
equilibrium constant.
What does equilibrium constant tell us?
It's a very small number, so it's excuse me, heavily reactant favored.
So if we do a Gibbs free energy diagram, we have HF together over here, and we have H plus and F minus on the left side. It is a very small number. So the Ka, we'll talk about the A in a second, but that tells us that that equilibrium constant is less than 1, much less than 1. So the minimum should be on what side of the graph, the left or the right? The reaction lies to the left. Our K is 7.1 times 10 to the negative 4th. Much smaller than 1. Okay? So do we expect there to be a lot of these two in solution when we're done? It's going to be a little bit, right? 10 to the negative 4th means there's some, but if our initial concentrations, like Josh said, are 0.50 molar, 0, and 0, where are we on this diagram? Where is our Q? Our initial Q is all reactants, no products. So we know that in order to get to equilibrium, we have to use up some reactants and generate some products. We have to move a little bit to the right to get to that equilibrium constant. Everyone follow me so far? This sounds really trivial and really simple, but it is one of the biggest stumbling blocks in ice tables. Because we're going to use that in order to determine the sign of the change part of the table. So if we go back now to the table, why did I put a minus x under 0.50 molar? Angel?
Reactants are being consumed.
Why? Why are reactants being consumed? How do we know that?
Yeah, because the products haven't been made yet.
Okay, so there's nothing to use up here. Fair. What's the other reason that we just talked about the diagram? Austin?
Wouldn't it be that we know that the constant is like a little bit less than the initial molarity?
Kind of, sort of, Colin?
Q is less than K.
Okay, so if we go back and we look at this diagram, we are over here. In order to get from here to the minimum, no matter what the minimum is, if we're slammed all the way over the far left side, we have to consume reactants, minus x on the left side of the reaction. So then what is x going to be on the right side? And what about under F minus? Is it always minus on the left and plus on the right? When you have a question like this, it is. When it says you're starting with all reactant, then yes. But a lot of times you're not starting with all reactant. You might start with a mixture of reactants and products. And then you have to say, well, what is Q? Where am I? Am I right at the equilibrium? Am I left at equilibrium? What's going to happen to get to equilibrium? So it's more complicated than that. Is it always a 1-to-1-to-1 ratio?
No.
What changes that ratio? Stoichiometric coefficients. All right, so all these things are going to come together. You're going to see more and more how we do that today. But it's all going back to reinforcing Q and K, which is what you have on the test. So hence why this is supporting what you're doing and ideally not new. So after we take our 0.50 molar solution, we lose some, then our final is 0.50 minus some. What are our final concentrations of H plus and F minus? Just, they're X's, right? So then what do we do now? How do I figure out what this X is? It'd be really nice to know, because that's what the question's asking, right? The whole way as we're going through this, I really want you to stop and say, what am I trying to find? A lot of times students just, okay, I'll solve for X now, and they have no idea what X is, and X isn't actually what's being asked for sometimes. So how do we solve for X?
We use that equation up top.
We use which equation up top?
The one that we have up there with K.
All right, so we know that Ka is the concentration of products raised to the stoichiometric coefficients over the concentration of the reactants, just like any other K that we've done before. So if we do that and we plug all of our numbers in, we put in the concentrations. We have on the top the concentration of H plus times the concentration of F minus is X squared. The bottom is the concentration of the initial minus, it went down a little bit, right? So at equilibrium we have 0.50 minus a little bit. Who likes doing the quadratic? Raise your hand.
We struggle.
Have you guys figured out how to not do the quadratic yet?
I haven't figured out the quadratic.
What if I told you that I never will test you on doing the quadratic? Is that a good thing? It's a waste of time.
You'll have to test us a different way.
You will have to use it sometimes. What's that?
You'll test us a different way.
I will. And it's actually harder. Students hate this. You have to approximate.
I'm good at that.
Okay, so that's where we're getting into. All right. We started off this whole conversation by saying, is that K big or small? What did you say? So is there much that's going to be broken apart and become these two? No. That's the approximation you have to make. If it's a really small amount, if it's less than 5%, we'll come back and check in a minute. If it's less than 5%, then I'm going to say, to hell with you. I don't care. It's basically going to be 0.50 molar anyway. It might be 5%, up to 5% less than that. But as long as we can say that this is going to change so little, then we're going to ignore it. We have to check it. We're going to ignore it for now. Can I ignore these x's?
No.
Okay, we can't ignore these because they are literally, it goes from 0 to something, so we can't ignore the something that it becomes. So then what does that equation become? Becomes x squared over 0.50. Can you guys solve for x there? All right, I think I have this written down in 2 steps. All right, so now go ahead and answer this question. Click in your answer, please. And I should have done it alphanumeric, so you have to enter the unit. So think about the unit when you enter your answer. If you've already done the quadratic, please do it with the assumption and compare the two so we can see how close they are. All right, a couple more seconds for you guys to enter your final answer. Remember to be very specific about what is x. What are you solving for? And then check to see if your answer makes sense. What do you expect the number to be? Is it bigger or smaller than a certain number? Can we approximate where it should be ballpark?
It's literally like, you do like the quadratic, it's like.
Yeah, let's hold on one sec. We'll get back to that. I want to hear both of those numbers though. All right, 41. I think that's it, right? Everybody clicked in? Let's take a look at our answers. So I see a variety of different numbers. What's the difference between the two biggest answers? The two most popular answers? This one and this one. How many sig figs should we have? We only have the certainty of 2 digits, so you should make sure to round your answer to 2 digits. All right, so using algebra, we rearrange this equation. We multiply 0.50 molar, that was our approximation, by our Ka. I came up with this value, and then how do we find the final value for x? Just take the square root of that, and I get 0.019 molar. Done, right? Wait, does that make any sense? How do I know? What am I comparing that to?
0.5.
Echo, what am I comparing to?
The 0.5.
0.50.
Yeah, 'cause it's more reactive favor, and because the K is a very small number, so you should only have a very small amount of product.
So if this number was bigger than 0.50, it could never happen. And because we said that it is mostly reactant favored, this should be a lot smaller than that number. How do we check to see if the approximation was valid? We made an approximation, right? Jonathan, how do we do that?
So we would go, like with the rest of the rice steps, I hadn't done the steps like the homework did, so it'd be step 4 where you plug in, where we have K, and we want to check the concentrations. X is going to equal the concentration H and F, and then the 0.5 minus the X that we got is going to give us a concentration at H, F. We'll just see how close that is to K.
So you're saying that we could plug in X in those two locations and see if it spits back out K. Did you do that?
No.
Okay, we could. Totally true. There's a quicker way to do it as well, love.
Could you just divide that X by 0.5 and see if it's within 5%?
Okay, so you can either do it that way or the other way around. We need to see if this is less than 5% of our initial concentration. So check that. See if it's valid or not, if you haven't done that already. Whichever way you want, figure out if that is less than 5% of our initial concentration.
Where does 5% come from? Why do we have that magical number?
Because everything ends up in a logarithmic scale, and so that's a number they decided is insignificant once you go to a log scale. I'll show you that in a minute. So what did you guys find? Thumbs up, thumbs down? Is the approximation valid? Is it less than 5% ionization or not? Or do we not know how to find if it's 5% or less? What are the two ways? So Love said one way is, so you could say, what is 5% of? And that would tell us what 5% is. And if it's less than that, we're fine. Did someone do it a different way? Ruby?
0.019 over 0.50 gives you 3.8%.
And then times 100, right? 3.8%. And you could also say this is 5% of what? So you could divide this, I think, by 0.05. Is that right? And I think that would give you what it would be 5% of. So lots of different ways you can do it. However you want to convince yourself, make sure that you check. On a test, exam 3, if you do not show me you check your approximation, I will be very unhappy. Avery?
So what would we do if it came up being wrong?
Then you would have to do quadratic. However, let me throw one thing out there, and I'll have to reiterate this because you guys will want to do this. Then the answer that Avery might give is, well, screw that. I'm going to do the quadratic every time. No. I will also ding you if you do the quadratic. You need to learn to approximate, and you need to learn to check your approximations. It's actually one of the skills we try to build in general chemistry. Students, if you've been through certain schooling, you're very comfortable with exact numbers and knowing exactly what the procedure and the steps are, and we got to wean you off of that because you need to approximate a lot of stuff when you're in work. So this is one of the places where I will require you to show that you did the approximation and you checked the approximation. Sounds ridiculous, but trust me, it is valuable. All right, and I think I have the rest of the steps written out here. Including the approximation. All right. What is the pH of that solution? Go ahead and click in your answer.
That's not would it be
All right, so we have 15 responses. Does that mean that we're not really comfortable with going from concentration of H+ ions to pH? If not, that's fine. We're just about to start using that a lot. So, pH, what does that P stand for, and what does the H stand for? What is the P? What's that? Not quite, not in this case. Essentially, the P stands for what's the power. So if we said our concentration of H plus ions, what is it, 0.0. In scientific notation, that's 1.9 times 10 to the... So essentially what we're saying is, what is the power? And so in order to go from pH, from the concentration of that, P means negative log. What is the negative exponent of this value? The reason last week I gave you a log quiz is because I need you thinking about how big is that number and how do we convert that into logarithmic values. What does the H part of pH stand for? H plus, concentration of H plus ions. Alright, so the pH is the negative log of the concentration of H plus ions. So what are we going to approximate that value to be? 2. Is it going to be a pH of 6? It's going to be somewhere close to 2, right? It's going to be a little bit above or a little bit below 2. What do you guys find if you do that calculation? Alright, so I want you thinking about what logarithms mean and what they do. The negative log means what is the negative power of that concentration of H plus ions in this case. What about sig figs? How many sig figs is that? Why? What does this first digit tell us?
Oh, it's in the pH, that's right, those don't count.
If I'm talking about this number here, does this 2 play a role in how many sig figs I have? These are the significant digits. So in a log scale, the ones place tells you something about this. And then the numbers past the decimal tell you how accurate your value is here. So I want you thinking on a logarithmic scale, the ones place tells you what is the exponent, the negative exponent of the 10's power. That is not a significant digit, so we're not counting the ones place as a significant digit. Let's do another practice. All right? We got a multiple choice question. Are you guys ready? And go. Which one of these is 3 sig figs?
Because
15 more seconds. Okay, almost everyone's clicking. Check with your neighbors, see if you agree with other groups around you. Real quick, check. And closing out.
I was just saying you would have to move the decimal and make it.
Why? Can you get another one that you know?
I was like, I'm going to
Come back. Why? Why is B the only one that has 3 sig figs? Matt?
I'm going to take a shot at it. Because if the ones place does not count as significant figures at any point in time, then I would assume that all the decimal places would be significant.
Correct. So how many sig figs does answer A have for the pH? 2. What about answer C? 4. All right. So what is pKa? What does this mean? Negative log of our equilibrium constant for this particular dissociation of an acid. POH. Negative log of the molarity of hydroxide ions. And we're going to be dealing a lot with that in the next couple of weeks when we talk about acids and bases. All right? So that log quiz that I gave you, which is actually being handed back right now, I do want you looking at what you got wrong. Go back and watch the video of anything you didn't get, because I am going to be expecting you to be very confident with logs moving forward. All right, so if we look at the sig figs here, I lost you guys. So remember to go backwards if we had pH, because P is a negative log of H plus ions. Then we could undo that to find the concentration of ions. So it's 10 to the negative pH would give us the H plus ions. So that would be, because we had 2 sig figs here, then we know the concentration with 2 sig figs. And this 10 to the negative fifth comes from here. Right? If this was a pH of 4.00, this would be a 4. But because we're slightly above or below, then it's going to be, I want you to be able to approximate plus or minus 1. So if it's a 4 here, you should be able to say, well, it's either a 3 or 5. That's reasonable. And then from there, make sure your answer makes sense. All right, and then if we have Ka, the same thing. So then our Ka value is going to be 3 sig figs because we had 3 past the decimal. And that's a way of writing it non-scientific notation. Concentration of hydroxide ions, 4 sig figs, and 4 past. All right. Questions on scientific notation, or sig figs really, and logarithms? You guys happy with this? Hopefully, since I forced you to become a little bit more confident with logarithms, hopefully it makes a little bit more sense. All right. Go ahead and determine the concentration of this solution of hydrochloric acid. I'll give you guys 1.5 minutes to answer this question. Careful. What's different about this question from the last one? Concentration is not the same. All right, we're at 1:30. We're doing the approximation. What's the only thing that we're changing? Raise your hand if you want 30 more seconds. Stop letting them.
There's the one from next.
referred to the tree that we worked here, and I saw, assuming we're using the same plate, and I just changed this to that one. So I multiplied it, got that, and
All right, how are we doing this? What's the setup? Can I get a volunteer to talk through it? New volunteer. Aurora? Or you've already talked as well? I've already forced you to talk. Question, Austin.
Are we assuming the same K?
So this is the same acid, it's the same temperature, so we're assuming the same Ka. Correct. So can I get someone new to share how to walk through this? Who hasn't shared their thoughts yet today? Savannah, can you talk us through your approach?
Yes, I did Ka is equal to, just everything's domain here. It'd be x squared divided by 0.050 minus x, and then you could leave off the x if you're still doing it the same way.
Okay. And then that still equals, what was it, 7.1 times 10 to the negative fourth?
Yes.
And then we solve for x. So what did you get when we solve for x?
I got 3.55 times 10 to the negative fifth. I don't.
I'm not sure that sounds right. David?
So that's what you get when you leave the x squared. So x squared equals that and then x squared right there.
Oh, yeah.
And then what did you find for the value?
Found 5.95 times 10 to the negative 2.
Which is also 0.
3.
Oh, say again, what's 3?
Negative 3. And then
Pause. And then the next step is? Negative, nope, not negative log. What's the next step? Make sure the approximation was valid. Is it less than 5%? No. So we would have to do the quadratic on this. So a good exam question for exam 3 would be, do you have to do the quadratic or not for this problem? That could be an exam question.
So basically, if it's above 5%, then you should do the quadratic.
If this ends up being more than 5% of our initial, it means that this approximation is not valid, and we have to be more accurate.
Okay.
Do you want to hear a really cool way that you can actually get around the quadratic, though? Well, even if our approximation is not valid, you can do something called the law of approximations, I think it is, where you take this number and you plug it in here, and then you solve for that x. And then you take this number, the new number you get, and you plug it in there, and then you solve for x, and then you do it again. So you keep getting closer and closer and closer to what the actual value of x is by plugging in what the change is. It's kind of fun. All right, so you would have to use quadratic for this, or the law of successive approximations. All right, so then let's think about that big picture. What happens to percent ionization? Think about that means as the concentration of these acids decreases. So make sure you're comfortable with the terminology. Talk to your neighbor to make sure you're comfortable with all the terms. And then think about the patterns. Couple more seconds, and then make the selection.
Oh, and if he's reading backwards, yes. Right? Yes. I don't think
Maybe it's 'cause I'm not used to it.
So let's talk about the terms. Which terms are maybe not super clear in the question? Are there any terms that are not clear? You guys are comfortable with all the terms? What does percent ionization mean? What's that, David?
Is it how much it dissociates?
Okay, why? So the answer is yes. Say again?
The ratio.
If we go and take a look at all these other reactions we were talking about, it's a terrible idea. Are there ions on the left side? Are there ions on the right side? The percent ionization is what percentage of it ionizes. So that's the terminology that I want you guys using here. So for this graph, for the reaction we just talked about, we just did two calculations. One at higher concentration, one at lower concentration. Which one had a higher percent ionization? The more dilute of an acid we looked at, the same acid, the same Ka, the more dilute it was, the higher the percent ionization. Does this graph show the same thing? As the concentration goes down, the percent ionization goes up. So we had, so which of these answers aligns with that? A. I'm looking at the clock and I'm thinking we're going to go to who loves gems? Who's from Arkansas and loves gems? I feel like it's a very Arkansas thing, right? So what we're going to talk about in the last 12 minutes of class is another form of our equilibrium constant. You're not going to change anything you've been doing. We're just going to give it another name. And we'll talk more about Ka and why it got its name. We'll do that in supplemental instruction this week, and then we'll build off of that on Monday. So what I want to talk about now is how these things form. And in order to do that, you kind of have to talk about solubility. So let's think about this image. Which one of these could be in that image? A couple more seconds. And closing out. So what you guys are telling me is that you have never, half of you, have never seen salt at the bottom of a glass. Is that true?
Or sugar.
Or sugar. Sugar is very soluble. Table salt is very soluble. But what we don't see here is how much is dissolved here. The soluble compound will have a much higher degree of sodium and chloride ions floating in here than the slightly soluble compound, calcium hydroxide, will have some ions, many fewer. And then the final one is insoluble, will have very, 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 very few ions floating around in here. And so remember this table, solubility chart?
Yes.
All right, and so then I've said, don't worry about it, it's either soluble or not soluble, kind of just like this hand-waving crap. Well, now we're going to talk more realistic about that. It's an equilibrium process, right? It's either a solid, it's not dissolved, or it's aqueous, and it's dissolved. And here, what they did, if you notice this little part, insoluble is less than 0.05 molar solubility. So you can have compounds that are slightly soluble that are actually white here, or really soluble that are white here, or insoluble and they're gray here. And so we're going to get rid of this all or nothing kind of mentality, and we're going to talk about the different gradations of solubility. So it's not this all or nothing. Here's kind of our definitions. Soluble compound is greater than 0.5 molar solubility. And then remember this cutoff that we had, the 0.05 molar, 50 millimolar. That's in slightly soluble, between 50 millimolar and 500 millimolar. And then anything less than 50 molar we're going to say is insoluble, even though it does have ions that exist in solution. That's an equilibrium process. So let's write an equilibrium constant. Go ahead and write the equilibrium constant for this reaction. And this is problem 12. Does anyone want to write it on the tablet? This guy.
She can. I did it last time. I had like age left.
Hannah, you want to write it?
Sure. Oh, everyone can judge my handwriting.
Want me to answer?
Oh, it's my little brother. Oh well, he can live with it.
Thank you. All right, Hannah, can you describe why you wrote the equilibrium constant the way you did? What did you include? What did you not include?
Okay. So I did products of the reactants, and I did the concentrations of those. That's why there's the brackets. I also included the charges just because the homework likes the charges on it.
So where's your reactants?
Because it's a solid, you don't actually include them, but you do add one.
Did everybody remember to do that? Okay. So we do not include solids in our equilibrium constants.
So it was either on the homework or the pre-class quiz, there was like L, so like liquid. So like why would that not be included with this?
Liquids, yeah, it says it's something different.
This is not included either.
Let's spend some more time on that next Monday when we start talking about acids specifically. It'll be a lot easier to talk about in that context. It's actually some of the slides that I skipped for today, just looking at the time. In essence, what we want to focus on are what are the things that are changing a lot. And if you have your solvent and you're describing the concentration of that, then everything else is going to be muted out by comparison. That's the short answer of it. So here, this is exactly the equilibrium constant. And in chemistry, we like to make things specific. That's KSP. Solubility products. Okay? Is that hard? A lot of classes teach it as, now we're going to talk about solubility product of salts and insolubility. And it's really just K. So you guys know how to do this. It does get a little bit more difficult once we start doing ice tables. But if you follow the same rules you've been doing, it actually doesn't end up being that difficult. So if we look at these two compounds, which one of these do you think is more soluble? Go ahead and click in your answer. Talk to your neighbor. Couple more seconds. We just had these two we're comparing. That's it. This is question 13. All right, and success. All right, so find someone that answered the other way from you. Try to think about it. What does that K mean? And try to figure out why one of these is more soluble than the other. By a lot.
No. So why would
You all said the same thing, so turn around and talk to them. Come on. Well, so be careful on top of the box. Sure.
they might be going for
I feel like I'm getting shorter every day. Is that why I have to like stand on my tippy toes to? All right, I'm going to freeze it right there. We did have a little bit of a shift during the discussion. Can anyone give us your justification for why one of these would be more soluble? Colin?
B has a higher KSP since we're only dealing with...
What?
B has a higher...
Oh, B does. Sorry. Yes.
Sorry.
I agree with you.
Yeah, B has a higher KSP since we're only dealing with products because the reactant is a solid. The higher the KSP means the more products we have. And so the more products we have in solution, the more soluble our reactant was.
What do you guys think about that?
Sounds logical.
Would anyone like to argue the other side? So I like the way that Colin focused on that. So if we look at what the KSP represents, for these it's going to be a different equation, right? We need to figure out how many ions they each have. But if we look at the initial one, the higher the number for KSP, the more of each of these we have in solution. If these are really, really, really small numbers, it means we don't have much in solution. The bigger the number is, the more we're going to have in solution. Could you write the KSP for both of these? The expression like that? What is the expression? Actually, let's go ahead and do let's do the last question before. Do we want to do this one? Let's do the very last one. Go ahead and determine the molar solubility of silver chloride. And in solubility, we're talking about how much is dissolved in the end of that compound. I'll give you a hint, use an ice table. If we know our K, we know the reaction, can you guys figure out how much is dissolved in the end? Looking at the clock. If we say we have no product in there to start with, the question is how much is generated? Is it going to be a minus or a plus X on the product side? There's nothing in there, so we're going to dissolve some. I'm intentionally going to leave the solid blank because we don't care if we're losing a little bit of solid. We're not worried about it for KSP. Why did I use S instead of X? Solubility. All right. So then, how do we solve for that solubility? Square root of KSP is the solubility. What's going to be different if we have different stoichiometry? So if we look at what if we had the first guy here? What's going to be different about that guy for an ice table than the one we just did. So the bottom of the ice table, we're going to have S for that guy, and it's 2S here. But wait. You end up using the stoichiometric coefficient once here and once there. All right, hopefully you can back out and think equilibrium constants. I got this. Concentration of products over reactants rates to stoichiometric coefficients. How does Q compare? What direction is the reaction going? I will see you guys Wednesday. Feel free to use discussion board to post questions.